All right, can you guys hear me okay? Too loud, too quiet, everybody good? All right, sweet. Well, I hope everybody's doing well today. It's a pleasure to be here. So my name is Dave Linville. We've got John Burnett with us as well, back there in the red shirt. I'm from Atlanta, Georgia. He's from Greenville, South Carolina. And we're here to talk about some water quality stuff and corrosion and do some chemistry experiments and all kinds of fun things. So before we begin, just a little bit of housekeeping. We do a lot of these talks, and the times that are the most fun are the ones where you all are the most interactive. And so if there's something that you want to go deeper on, something that everybody doesn't want to talk about, let me know. Hey, nobody cares about this, let's move on. That's fine. Be as interactive as possible and ask questions and participate. Our goal is to just help you guys out talking about water chemistry however we can. So whatever issues you're facing, feel free to bring them up. So with that, I believe it's really, really important, and you can't see it, it's really important to talk about core missions. This is something that we talk about in our team all the time. I think it's really important to kind of know who you're working with. And so our core mission at AquaSmart is real simple. Everybody deserves clean water. And what's interesting is the challenges that you all face are not new challenges. So how to control scale, how to not have corrosion, how to not have bacteria. These have been around for a really long time. And so why is that? I think there's two fundamental challenges to the drinking water business. We'll get into some of those here in a second. But before we get all into it, what do you guys see when you see this picture? What does it mean to you? Anybody take a stab? Sink the ship, okay. Anybody, what else? What's that? Customer complaints? Okay, yeah. Would have got away with it if it wasn't for those pesky customers.
Challenge.
What's that?
Challenge.
Challenge? Yeah, okay. Anybody who likes science fiction movies? I like science fiction movies. So the way that science fiction movies tend to start is man messes with nature and then ... How many premises have you seen where that's what happens? So how is this related to water treatment? Any guesses? What's that? Man is destroying everything. Okay. Yeah. Okay. Yeah, I follow that. Any other ideas? So the thing is I said there's two challenges to the drinking water business. Challenge number one is you've got to drink whatever you put in the water. So there's a lot of ways to not have all these problems, but you can't drink this stuff. It's not safe. So that is a challenge. The second challenge is over time, things get more complicated. Like how much, I'm sure you guys, even this afternoon, talking to the regulatory folks about the lead copper inventory stuff. The rules aren't getting less complicated. Like things get more complicated over time. And what ends up happening is you do something and then, well, now I did this, but because I did that, now this other thing happens. And so now I have to do this other thing, but then now this third thing happens. And it's this sort of like spiraling of consequences that ends up happening. And it's really challenging. I think it's really a difficult situation for you guys to face. So we like to talk about things that are related. And so things that are related to corrosion control are these things. You can read through those things, and we're going to open up the boxes and do our first demonstration to talk about some of these principles. So go ahead and open up the boxes, the white boxes in front of you. Okay, so what you've got in the box is you've got 2 jars of water, you've got 2 powdered pillows of iron, you've got 1 bottle of bleach, and you've got 1 bottle of SeaQuest. So the SeaQuest has the black cap, the bleach has the white cap. So what you're gonna do is take one of the bottles of water and take one of the powder pillows of iron, take the iron and dump it into the water and shake it up. Any ideas on what's gonna happen? Hey. Everybody get that good and shake it up? Start to get a little bit of yellowish to it, maybe? Okay, next take the white cap bottle, that's the bleach, and add a few drops of bleach in. You can add it like one drop at a time. It's kind of cool to see the chemistry. And then give that a good shake. So anybody want to comment on what's happening there? Iron is being oxidized and then precipitated. Absolutely. So if any of you guys have surface water plants, or you've got wells that have a ton of iron and maybe you're filtering it out, this is something that you would be doing on the front end of those plants, where the idea is you have minerals and metals and they're soluble, and then you want them to become insoluble so that you can filter them out. Okay? So let's go ahead and take the other bottle and go ahead and add about half of the SeaQuest to it. It's the black topped vial. We're going to use the other half for something else. It doesn't have to be that precise. Give that a good shake. Yes? It's a blended phosphate from a regulatory category. We'll talk about it at the end a little bit. Okay? Once that's good and shaken up, go ahead and take the second iron packet and dump it into the water that has the SeaQuest in it, and give it a good shake. If you get little white flakes, it means you haven't shaken it enough. What's that? No, the other bottle of water. That's that. It should have the SeaQuest in it from the black cap, right? Okay, get that nice and shaken up. Once it's good and mixed and you don't see any more particulate, go ahead and add the bleach to that bottle. Again, just kind of do it a couple drops at a time. Add 3 or 4 drops. So what do you see? Not a whole lot, hopefully. So what's going on there is called sequestration. So if anybody's heard of that concept before, that's what's happening. So the idea is if you have minerals and metal, you can add something that contains polyphosphate, and it acts as a chelating agent or a sequestering agent to keep things soluble and prevent them from being oxidized. So what's the difference between the jars? One of them is dirty and yellow. One of them is clean and not dirty and yellow. There's 2 things that are important about that. What do you think those 2 things are? What's that? One's soluble, one kind of. What's that? One's clean, one's dirty. So which one do you get the calls about? Right? So nobody wants to drink water that looks like that, is the first thing. But there's a second thing that's kind of related to some of this stuff. You guys can read through this slide a little bit and see if you can figure out what it is. I'll give you a hint, it's on the left side. One's going to degrade infrastructure, one's not. Yeah, I buy that. What's that? Yeah, exactly. Why is that? She said lower chlorine residuals. Yeah, so if you ran a free chlorine test on those 2 jars, which one has more free chlorine in it? The clean one. So what's the reason that you add bleach? It's to kill bacteria. It's not to oxidize iron. So if you have water that looks like that, yeah, there's some interesting things going on. Iron comes from 2 places. Either it comes from the natural water, which if you're on a well, we've heard, Western Carolina, I know in the coastal areas, we've got a lot of customers that have wells that iron them. So you could have some natural iron in your well that maybe you're not filtering out. So that could be a source of iron. Another source of iron is, steel pipes from the distribution system. So if you get some corrosion from the distribution system, you can put a small amount of iron in the water, oxidize it, and get something that looks like that. The other thing that then happens is corrosion's related to pumping costs, because if it's that second thing where you got iron from the pipes, well, who's seen corroded pipes, right? Everybody's seen corroded pipes. They got the tubercles, all around them. So what happens is it costs a lot more money to push the same volume of water through smaller pipes. So the more those pipes are constricted, the more inefficient the distribution system is, which leads to extra cost. We're going to talk about phosphorus a little bit, and then we'll talk about dangerous chemicals and overall total cost. We believe these are really important, holistic ways to look at all this stuff. So, the corrosion story. Back to our science fiction metaphor. Got to talk about things with a story. So who's seen something like this before? So this is the corrosion cell, an example of the corrosion cell. So basically you have 3 things that you have to have for corrosion to take place. You've got to have metal, you've got to have the flow of electrons, and you've got to have some sort of carrier for the electrons to flow. It's called an electrolyte solution. So that's what water is in this picture. So you got water, you get the flow of electrons, and you've got metal. And there's a lot of ways that you could not have corrosion. The predominant wisdom in our industry is to build mineral scale. And the idea is if you put down a thin barrier of calcium carbonate, looking at maybe LSI calculations, if you put down maybe calcium phosphate, feeding some phosphorus, the idea is to protect the pipe by putting a barrier layer of mineral scale on it so that the water and the pipe don't meet. That's the concept. The challenge to that is building mineral scale is really, really complicated because this is back to the 2 fundamental challenges of the drinking water business. 1, you got to drink the water. 2 is you get 1 chance to do something at the plant, and there's no levers to pull once the water leaves the plant. And what ends up happening is distribution systems are dynamic. They're not static systems. So pH changes, temperature changes, flow changes. You don't have control over all the variables. And all of those variables are inputs on how scale works. So you end up with a variable way of it working, basically, which makes it really challenging. So this is from the EPA. They gave a webinar in 2021 talking about lead corrosion. And this is a picture of lead pipes that are all coated with lead scale, phosphate scale. So what do you see that's interesting about all these pipes? What do you guys think? It's not uniform, exactly. And so, the EPA talks about this as well, where you can read, scale actually is really complicated. It's not uniform. So this again is from EPA. I love these slides because I think they're perfect. The idea is, wouldn't it be nice if we were able to make an adjustment at the plant, get the water where it needs to be so that it forms this thin layer of calcium carbonate and protects everything? That'd be really convenient if that worked. And that was sort of the predominant wisdom in the industry for a long time. And the reality is it actually looks like this. So what ends up happening is, again, because the distribution systems are dynamic, it doesn't work like that. You get these complexes where you have organic levels, you have various types of oxidation species of the metal. You have some phosphate, you have some calcium, you get this like matrix basically. And essentially, the concept of building mineral scale really doesn't work. So to sort of summarize, the idea of simply building mineral scale to control corrosion theoretically could work, practically is really challenging, and really would only work if you were starting with clean pipe under static conditions, which never exists in a real world distribution system. So then why do we add all this orthophosphate? How many people add orthophosphate to their system? A lot, right? So like, why do we all add orthophosphate? The idea is, for corrosion control, right? That's the reason. In reality, it's not about general corrosion control, it's about very specific lead control. I think that's what we've learned over the last 20 years, is that, again, adding orthophosphate to form calcium phosphate scale generally over a distribution system doesn't work, unless you have a brand new distribution system and you control all of the variables of the water in the distribution system, which never happens. So why are we adding all this phosphorus? Well, this is how lead works. So when lead corrodes, it kicks off lead 4+ and lead 2+. Lead 4+ is insoluble and stays adhered to the lead pipe. Lead 2+ is soluble and goes into the water. So when you guys hear in the news like somebody had a lead issue, it's a lead 2+ issue because that's soluble lead in the water that reaches the customer. So what happens is orthophosphate has an interesting characteristic in that if you essentially add enough orthophosphate, you're able to complex the lead 2+. And you drive this reaction to orthophosphate lead complex. And the thing about that is it's insoluble. And so it stays on the pipe. So that's kind of deep. Does that all make sense? So if you basically drive this reaction, the 3Pb plus 2 plus 2PO4, if you have excess PO4, then the idea is you don't have any lead 2+. That's the basic concept of orthophosphate. And then, then it becomes not disrupting this phosphate lead complex that you have on the lead service lines. And that becomes the main goal of corrosion control. And that's something that the EPA is talking a lot about. I'll pause there because that was kind of deep science stuff. Any questions on that? Okay. So how many of you guys have lots of lead in your distribution systems? Exactly. So we'll come to that in a second. To summarize orthophosphate, I think it's kind of a misnomer. EPA actually talks about this in that 2021 webinar, where orthophosphate is really not a corrosion inhibitor. The lead oxidizes and essentially corrodes, and then orthophosphate is an additive that complexes with the corrosion byproducts. That's the mechanism of how it actually works. So it's just kind of like wrong to think about it as a corrosion inhibitor. It doesn't actually inhibit corrosion. The lead still corrodes. You just deal with the byproducts. So back to the show of hands, why is that important? Is because most distribution systems aren't made of lead. They're made of steel. How many people have steel in their distribution system? Is it all PVC? What else do you guys have? It's not steel or PVC. What's that? Concrete? Okay. Yeah, ductile iron counts as steel. Okay. So basically, what happens is all this orthophosphate gets added, and it doesn't really work on pipes that look like that. Which maybe that's an extreme example of a pipe that's pretty far gone. But even if the pipes look a little bit like that, adding all that orthophosphate isn't really doing a whole lot because it fundamentally doesn't work because the pipe's not clean. And this issue sort of leads to a lot of downstream consequences, back to the angry space monkey. So the first thing is, get rid of that top thing. The question is, what if you use silica instead of orthophosphate? Exactly the same concept. Mm-hmm. Yeah, you're trying to form silicate scale, and it works on clean pipe, and it doesn't work on not clean pipe. Yep. So we raise pH Why? Generally speaking. Anybody know? Make the water less corrosive. So this is all rooted in LSI calculations and RSI calculations and these various indices. And they're all related to this thing called Baylis curve. Has anybody ever seen a Baylis curve before? So the idea is you control the pH and you control the alkalinity so that you're in that little medium blue zone. And if the water is in that medium blue zone, then it's neither scaling nor corrosive, is the basic concept. But again, it doesn't really work like that because the distribution system is dynamic. You don't control the water in the distribution system. You control the water at the plant, and then it changes in the distribution system. You guys mentioned concrete lined pipe. So if you have concrete lined pipe, if it's new, it definitely changes. Because like as you season that pipe, you pull out calcium and it drives the pH up. So you probably have areas in your distribution system that have pH swings, would be my guess, unless it's really old pipe. So then like, what do you do here, right? Well, pH is different, this spot versus that spot. So you can't really use this method because you don't have control over it. But then back to the orthophosphate. So the idea is the orthophosphate controls lead, and for the orthophosphate to work in that reaction, the pH has to be within a certain range. So that's one of the real reasons that if you're using orthophosphate, you got to get the pH above 7.2. So 7.2 to 7.8 is kind of the sweet spot. I think 8.2 still works. So what happens to chlorine as the pH goes up? Any ideas? What do you guys use for disinfection? Is it mostly bleach? Is it gas? Mostly bleach? Mostly bleach. Okay. Any ideas on what happens to bleach as a function of pH? It dissipates. Absolutely. You guys have seen this before. So this is the dissociation curve of sodium hypochlorite in water, which basically means it dissociates between a strong acid and a weak ion. So the strong acid is the HOCl, and the weak ion is the OCl minus. Okay? So you see how it's sort of logarithmic, it goes through that curve. So the higher the pH, the more weak ion you have, and the less strong acid you have. Okay? So why does that matter? Well, the goal of chlorine is to kill bacteria. And bacteria has evolved to want to not be killed. And so the way that it works is it's about penetrating the cell wall of bacteria and lysing the cell so that it dies. And the thing about it is the strong acid form penetrates the cell wall, and the weak ion form doesn't penetrate the cell wall. So basically, the higher the pH, the more weak ion you have, and essentially like you're wasting chlorine because it's in the wrong form. It needs to be in the hypochlorous acid form to kill bacteria. So then you end up needing more chlorine. That's why if you, to get a free chlorine residual, the higher the pH you go, the more chlorine you have to pump in on the front end. Which then can lead to all kinds of challenges with, if you're on a surface water system, you then have to maybe, go to chloramines because you got all of this organic material and you have too much bleach in the summer. It's back to this like unintended consequence thing of just leading to this complexity. So that's another interesting thing is there's a relationship between oxidation and lead. And I know you guys don't have a lot of lead, so maybe this is just more informational, but essentially, it's all about fully oxidizing the lead. You want it to be lead 4+. And chloramine is a weaker oxidant than bleach. And so what can happen if you're looking at switching to chloramine is you don't fully oxidize the lead, it comes off as lead 2+, and then you have a lead problem. And this is exactly what happened in Washington, D.C. in the early 2000s, if anybody remembers the huge national Washington, D.C. lead issue. So that's interesting to me because it's related to something called a pour-by diagram. Anybody seen one of these before? So it's kind of complicated. How to read this is every metal has one of these in the presence of water. And so it's all about how do metals oxidize. And so metals oxidize differently as a function of pH and electrical potential. So you can see the pH on the bottom, and then the left is the electrical potential or the ORP of the water. And so anybody remember Newark, maybe like 4 years ago, had a big lead issue, and now they've got all their lead service lines out of the ground. So what happened at Newark is they had a nitrification issue in a section of the distribution system that happened to be using silica, interestingly. And as a result, they got their pH dropped in a section of their distribution system. And that's this arrow, the blue arrow to the left up there. And they kicked off a bunch of lead because they moved in the phase diagram from the area of fully oxidized lead to the blue area that's not fully oxidized lead, where the lead is soluble. So at the end of the day, it should be a way to think about this stuff is, make sure the oxidizer is the strongest possible. So anything that can boost oxidation, back to our experiment here, anything that can boost oxidation has a direct impact on lead control. And anything that disrupts pH in the distribution system, the more variability you have in pH in the distribution system, the worse potentially that is for lead control. So it's about stability. We like to talk about health and safety. A lot of times phosphoric acid is used for orthophosphate, which is kind of nasty. All the pH adjustment chemicals are really nasty. And then total cost, there's an EPA paper that talks about total cost being important, which we agree with. I know I'm kind of flying through this, but figured to hit the summary. If anybody wants the presentation, we can send it. I think you guys have access to it after the fact, right? So.
Yeah, they'll get it in an email.
Okay, perfect. Yeah, so anybody has questions, just let us know. All this stuff's free to share. So this is an interesting quote, sticking with our science fiction theme about phosphorus. So I find that really fascinating. As sort of like a steward of the environment. And so the way that phosphorus works is over many, many, many years, phosphate goes down into the bedrock, and then it comes back up to the surface. We mine it out and use it for stuff, and then discharge it. And it goes through this big equilibrium circle. And so it's really important to not discharge too much of it. That's why if anybody deals with wastewater treatment, I'm sure that track, somebody's talking about, phosphorus limits. And if I'm not talking about it now, they're going to be talking about it in the next 5 to 10 years. Because it's all about not poisoning the lakes with harmful algae blooms and all this stuff that you read about in some of these areas. So being really responsible for our phosphorus, I think, is really important. So what's interesting is the EPA did a study that concluded as much as 35% of the load on wastewater plants to remove phosphorus comes from using phosphorus in drinking water plants for corrosion control, which is really interesting. So it's not an insignificant number. So at the end of the day, our basic concept is all this stuff's related. It escalates in complexity over time. Scale building doesn't really work. And the more chemicals and complexity you add to the mix, the harder everything becomes, because it just increases the stack of cards. So what we do is take a bit of a more holistic approach to water quality. So, back to the corrosion cell, if you think about corrosion, it's an electrochemical process. And the way we like to think about it is, if you imagine the corrosion process being this light, and your goal being not seeing light, one of the ways to not see light would be to cover the light with tape. And that's sort of like the idea of scale. It could work, it might be complicated, but you could make it work maybe. Another way would be just turn off the current to the light. And that's sort of a simpler way. And so what we do is essentially turn off the current to the light. We're going to go ahead and use the second half of the SeaQuest now. So take the second half of the SeaQuest and actually shake up the jar that has the dirty water. And then let it sit there for a second. And then add the SeaQuest and don't shake it. And what you'll see is the SeaQuest is heavy. All these water treatment additives are all 1.3 specific gravity plus or minus. So it's going to sink. It's going to sink down to the bottom of that jar. And then over the next 15 minutes, just kind of watch what happens. And what we're going to be talking about is the concept of charge. So remember, the SeaQuest is really heavy. It sinks to the bottom. It's strongly anionically charged, which means it wants to react with things that are weakly cationic. And so that oxidized iron is weakly cationic. So what you should see is, at the very beginning, the SeaQuest is going to be down at the bottom, and then over time, that's going to migrate up as it sort of seeks out things that are weakly cationic. If you shake it, it won't do it because it'll get all mixed. But you'll kind of see that, every jar is a little bit different. Sometimes it takes 10 minutes, sometimes it takes an hour. But I think it's an interesting experiment to show how sort of charge works. So what the SeaQuest is, it's a blended phosphate. This is polyphosphate on the left, orthophosphate on the right. And what happens traditionally with blended phosphates is you're relying on something called hydrolysis to make more orthophosphate. That's the top gray arrow. And the idea is, well, orthophosphate does corrosion control, so polyphosphate does iron control. If we do that at the plant and then we get a little bit more ortho out in the distribution system, that's good for corrosion control. We've already kind of talked about that doesn't really work because it just doesn't really work that way unless you have significant amounts of lead where it really does work. But absent lots of lead, you basically end up depleting polyphosphate and building orthophosphate for no reason. So what we figured out how to do is drive that blue arrow to happen. So there's a third ingredient in SeaQuest that acts as a chemical catalyst that drives that reaction. And what we end up with is a constant equilibrium between ortho and polyphosphate. Why that's important is when that blue arrow happens, we end up consuming free radicals at the cathodic area of the corrosion cell. So that's how we're sort of attacking the corrosion cell electrochemically, because we're starving the cell of a needed ingredient to function. Make sense? So the result is, if you look at traditional, chemical selection, you can see it's all about, controlling lead and copper is clearly very important. Controlling steel is important. Looking at color and appearance is important. How much do you use and how much does it cost? We like to look at this more holistic way, where it's all about responsible phosphorus use. We do contain some phosphorus, typically much less than other methods, but we do contain some. And then it's all about how do you boost chlorine residuals, as we saw, in that jar. It's really important. And at the end of the day, safety and total cost is really important. So we touch all of these issues. Our website has all of these as different pages. So if anybody's curious about any of our stuff or just wants to learn more about chemistry in general, you can go to our website and each of these has a page that talks about well, why do you have, hard to control chemicals? What actually leads to that? And then we've got some stuff about us that talks about case histories, but there is really good scientific descriptions of everything. We've been around for a long time. We treated a little over 8 trillion gallons of water. We get a lot of letters back from our customers that we appreciate. And then something that we use with regulators a lot is, well, it's got to work to control lead. You guys don't have a lot of lead, so maybe this slide isn't as important to you. But basically what we did was we looked back for the last 20 years and captured our customers that switched from something other than SeaQuest to SeaQuest. What happened to the lead as measured by the 90th percentiles? And this box and whisker on the left shows that the lead numbers went down for the customers that switched to SeaQuest. And then the one on the right shows as the customers adopted SeaQuest, the number of customers went up in orange. And then the lead numbers, steadily went down over time, never approaching 10 or 15. And then sort of back to the UK, these are some projections from Bristol Water. We do a lot of work over in the UK. I'll talk about them here in a second. And the idea is in the UK, they've made a commitment to be carbon neutral by 2030. And so one of the major users of carbon is all of this pH adjustment chemicals. And so you can see, if you take those away, that's the bottom row here, how much less carbon there is that they're going to consume. That's the third column. But then if they switch from phosphoric acid to SeaQuest, here's how much less phosphorus they're going to use. So we're in some studies right now with them. Then here's some case histories. Before that, I'll kind of pause for questions. I think we got about 10 minutes left, so open up questions and then maybe talk through some case histories. What's that? Does the SeaQuest cause a byproduct? No. Yeah, you're going to sequester iron and manganese. It's going to stay soluble, and then ultimately, get flushed. So no, once the reactions happen, they don't go back. I guess theoretically they would if you let that water sit for weeks, but on a practical basis, no, it's always forward.
Dave.
Yeah.
I have 2 questions.
Sure.
First one, so if iron and manganese are remaining soluble, is there, if somebody's doing like a load of whites and they use bleach, is it going to come out and cause dirty laundry?
No, that's where one of my favorite case histories talks about that. Yeah, the middle bottom there. Yeah, we had a customer in Mississippi that they used to have that problem.
So it stays sequestered even after
Yep.
strong oxide.
Yeah, actually, this is, let me skip to this one. Let's cruise this in here somewhere. Oh.
Oh, are you anywhere in North Carolina right now?
Yes.
Is this product in use?
Yep, absolutely. Yeah, we just started with Pender County. We've got Piedmont Tri as a customer, Aqua North Carolina as a customer. John can go through some more as well. Rocky Mount started on Monday. Screen sharing is stopped. Okay. Can I share my screen again? I think we may have lost the people online in screen sharing. So this, we do work in Las Cruces, New Mexico, and this kind of answers your question. It kind of answers your question too about long-term solubility. So what this shows, we've got a full case history that's got more details, but essentially what a consultant in New Mexico wanted to figure out was how do you evaluate these things based on their ability to keep metals sequestered for long periods of time in the presence of strong oxidizers? Because ultimately it's like, well, everybody says whatever, but like how do you get like a scientific test that sort of shows that with real data? And so they did this study where they took their raw water. They've got a big field of wells in Las Cruces. It's like 80 different wells, and a bunch of them have manganese, and a bunch of them have iron, and they don't remove them. And they use bleach as their oxidizer. And so they take the water, they dose it with the additive, and then they dose it with bleach, and then they let it sit there and measure it at different periods of time and filter it through 0.45 micron filter paper. And the idea is, if you come out of solution, you're going to see it on the filter paper as it becomes insoluble. And you can see that here with the pictures of the filter paper over time. So the longer the time goes, the more aggressive the test is, because that's the longer contact time with the bleach. So you can see the SeaQuest works the longest, and it works at a lower dose. You can see the 1.2 compared to the 2 ppm of different blended phosphates. So that kind of shows that mechanism in action of like constantly replenishing the polyphosphate. And based on this test, we were awarded the business at Las Cruces last summer. And we've got a full case history that talks in more detail about that. But does that answer your question too?
Perfect.
We can do this test in our lab. So if anybody has any interest in doing water tests, we've got a lab in Atlanta, happy to do whatever test you want. We do corrosion studies, we do coupon analysis, we do this kind of test, we do all kinds of stuff. So, yes?
What about systems that might have legacy iron and manganese?
It's a great question. So that's the question that we always get.
Could you repeat the question?
The question is, what happens to systems that have a bunch of stuff already in the pipes? More or less, right? Yeah. So the best way to answer that is taking a trip over to the United Kingdom. Got it. So the thing about water in the UK is they dose high levels of orthophosphate in areas of their distribution system that have lots of lead. And they dose like 4 to 6 ppm as orthophosphate, so massive levels. It's one of the things that the EPA is trying to figure out with the lead copper rule to maybe mimic the UK, which when you have areas that have tons of lead makes sense. When you have areas that don't have tons of lead, it doesn't make any sense. So the UK has figured out to isolate zones in their distribution systems that have tons of lead service lines, massive orthophosphate, and the other areas they basically don't do anything. They changed the pH and let it ride. And they live with massive discoloration complaints. And that was fine up until about 2004, I think they started studying it, yeah. So in 2004, DWI, which is the equivalent of the EPA at the federal level, said, well, look, we got to do something about these complaints. And so you can see in 2015, there were 6,000 complaints. They actually track complaints. It's a regulated thing in the UK, which is a little bit different in the US. So the UK is a little bit more restrictive. So there were 6,000 complaints, and 13% of them were in and around London. And so the London utilities needed to figure out how to do something different. So one of them is called Southeast Water. That's our customer. And they've used the SeaQuest in an area east of or west of London for a long time and solved discoloration issues. And they started using it in the eastern side in 2017. And you can see here is the case history from the eastern side. So you can see complaints went down, not all the way down. We're currently optimizing this to try and get them even lower. But the interesting thing about it is the way that the UK utilities are regulated is they have to track iron and they have to track lead multiple times per month continuously. It's not once every 3 years. It's multiple times per month continuously. And if they have a lead number that is above 10, that's a violation. A single data point above 10 is a violation. So it's extremely restrictive in how they're measured. And what that gives us is a significant amount of data to look at. And so this picture on the top right is really interesting. So what this shows is the levels of iron in the distribution system as measured by, I think it's 10,000 iron results are behind those curves over that many months. So you've got a year's worth of data, and what it shows is the 2 years after they started using SeaQuest, the iron stayed the same in the water. It's really low, so that's micrograms per liter, so that's like 0.04 ppm, 0.02 to 0.04 ppm. So it's not a lot, but there's a little bit of iron that's coming from corrosion, and that's why they get the complaints when they oxidize it. So we saw the complaints go way down in that two-year period, and we see iron stay the same. And then we see iron go down in year 3, which is really interesting. Because what actually happens is in areas that are really foul or have lots of tubercles or have lots of manganese or whatever, we encounter that a lot. And so 2 things happen when you start using SeaQuest. One is those tubercles are sort of deactivated so that less iron goes into the water from the tubercles that you already have. Think about the difference in iron from 2017 to 2021 being that measured. So there's less iron that's going in from the tubercles. But at the same time, we clean up the tubercles and slowly remove them to get back to the pipe the way it should be. And that's why we see the iron stay the same in 2018. So the net effect is basically the same level of iron for a couple of years and then a drop off in iron as we get the tubercles under control while seeing a reduction in complaints. So the customers never see the impact of any of this. Does that answer your question? And we've got similar studies about manganese. There's a lot of manganese down in Louisiana, so we do some work down there that we can talk about as well. Any other questions? Yeah. We good with questions? I don't know how we're, good. Yeah, sure.
What is the process?
Yeah, so the process is typically, it depends on how much orthophosphate you're dosing, but typically we utilize the same feed equipment and same everything. Clean out the orthophosphate system, flush it with some water, and just use SeaQuest. John comes out and does a full system audit, and we've got a calculator that looks at dosage and all of that. But at the end of the day, usually we're using less material, so you got to turn your pumps down. Typically, it's different everywhere, but typically you're a little bit less. So you just got to make sure your pumps can go low enough and stay reliable. That's the only real impact.
Hey, right? The end of the ground.
No, yeah, we deal in really old systems. We got a lot of customers up in New Jersey that have 150-year-old pipes. Yeah, no, UK, right? I mean, even older than that. So they've got Roman pipes still. So they all have lead. So no, yeah, no concern over pipe age. So we get back to, yeah.
Yes, Has your company, done any testing to see if there are any byproducts from your?
Oh yeah, so like how safe is it basically?
Right.
Yeah, so we use all food grade ingredients. It's all phosphate salts, and so it's the same thing that's used as preservatives in all food basically. We calculated out one time that we have, if you drink water that has SeaQuest in it, you're consuming like 10 times less phosphate salts as if you drink a bottle of Coca-Cola, just as a relative amount of phosphate salts that we're talking about. So it's all the same family of chemicals. Bread, anything that has a shelf life extension in a grocery store has all these kinds of things in it. And to be fair, that's the same thing with orthophosphate. So that's the same answer for all of these types of additives. They're all real safe. Yep, one more? Yep. It might. So what's your, is it all PVC distribution system? Huh. Okay. Yeah, so the thing, I'm not sure if we can help you or not, to be honest, but the in areas that you don't have any complaints, there's really no cost savings from taking something away and replacing it with something that you use less. We talk about chlorine. That could be something to look at. I don't know if you guys look at the free chlorine at the plant versus the free chlorine in distribution. What's that? Yeah, so we typically see, you can go to our website and there's a lot more case histories about that, but we see an increase, if you keep the level of the plant the same, we typically see a pickup of the free chlorine in distribution. So you can end up using less at the plant, or if you have areas that are really hard to get residuals in distribution, we can make it easier to get residuals in distribution. That would potentially be something. Yeah, oh, maybe one last one.
Have you seen any results from any reactions with certain doses of fluoride?
No, I haven't. We've got probably 400 customers in the U.S. and I don't know how many of them use fluoride, but I know it's a lot of them. And no, we never see any reactions with fluoride.
So you haven't done any studies, or you haven't?
We haven't done any studies. I haven't done any studies. I don't personally know of any information. I just haven't ever seen it be an issue. So, all right. If you guys want to find us, website, John's in the back. He's got a booth. Happy to help you guys however we can. Make clean water. So.
Oh, that's great. Oh, that's perfect.
It depends on what you're using, so it's hard to answer that, but usually the total cost is less. So it just depends. If